example. So now we're going to do the same thing with example 2 and the Simpson's rule error bound estimate. Okay. All right, so the first thing we're going to do is find the upper bound, which means first we have to find m. All right, now with Simpson's rule, m is an upper bound on the fourth derivative. So unfortunately, I have to find the fourth derivative of f of x equals x plus 1 to the negative 1/2. All right, so I'll do this kind of quickly. F prime of x is negative 1/2 x plus 1 to the negative 3/2. This is actually kind of good practice for something we're going to be doing towards the end of chapter 10. Negative 1/2 times negative 3/2 is 3/4. X plus 1 to the negative 5/2. F triple prime, 3/4 times negative 5/2 is negative 15/8. X plus 1 to the negative 7/2. And then the fourth derivative, negative 15/8 times negative 7/2 is 105/16. X plus 1 to the negative 9/2. Yuck. All right, so we have to figure out how big can this thing possibly get on the interval from 0 to 3. And to figure that out, it might be easiest to rewrite this as 105/16. And then 9/2 power. What does that mean? It means the square root of the 9th power, right? So we're in a situation sort of like in the last example. We have a fraction with the variable in the denominator. So if we want to make this expression as large as possible, we need to make the denominator as small as possible. So that's going to be when x equals 0. So this expression is largest when x equals 0. M, which is the absolute value of the fourth derivative, and in this case at 0. Well, when you put 0 in for x, that radical turns into the square root of 1 to the 9th, which is just 1. So fair to say that m is 105/16. Okay. And if I wanted to, I could round that up to the next whole number if I was trying to make my calculation simpler. But because remember, m is an upper bound itself. It doesn't have to be the exact largest value of the fourth derivative. It can be anything bigger. But, you know, keep that upper bound as tight as you can, because then it'll give you a better value for your error estimate. You want your error estimate to be small, right? Okay, so once again, I did not leave myself any room to finish this part of the problem. So let me erase some stuff, I guess here. All right. So let me use this area over here. Okay, the error in Simpson's rule is guaranteed to be less than or equal to m, which is, you know what, I think I'll put in a decimal for that. 105/16 is 6.5625, which again, I could round up if I wanted to, times b minus a to the power 5 over 180 times n to the fourth. This one I don't think I can do just by crossing stuff out. I think I have to actually crunch these numbers. So 6.5625 times 3 to the 5th divided by 180 times 4 to the 4th. All right, I get that that error estimate, or that upper bound, is 0.0346. So guaranteed, if you use Simpson's rule with n equals 4 subintervals to estimate the value of this integral, that estimate will be off by no more than 0.0346. So that's a lot better than 1/4 in the last example. Okay, and so let's see what it is actually. So now we're going to calculate the exact value of this integral, and so we can find the exact error. Okay, so integral from 0 to 3 of x plus 1 to the negative 1/2 by the backwards power rule is x plus 1 to the 1/2 divided by 1/2, which is the same thing as multiplying by 2. All right, so we have 2 times 3 plus 1 to the power 1/2 is the square root of 4. 0 plus 1 to the power 1/2 is the square root of 1. We're talking 2 times 2 minus 1 is exactly 2. If you look back at example 2, the Simpson's rule estimate was 2.0019. I remember thinking at the time, I bet the exact value of this integral is 2. So that means that the actual error is 2.0019 minus 2, which is 0.0019, which is less than 0.0346. So that upper bound on the error is working. All right, there was one last part to this problem, a completely new problem. This was to find the minimum n. Let me write the, or at least summarize the instructions again. Find n so that the error in using the trapezoidal rule is less than or equal to 10 to the negative 4. And I think we were supposed to do the same thing with Simpson's rule. I'll check that before we actually do it. Okay, so first I have to find the value of m. Now, when you have a cosine or a sine, that's actually very easy. F of x is the cosine of x plus pi. So f prime of x is negative sine of x plus pi times the derivative of x plus pi, which is 1. The second derivative will be negative cosine of x plus pi. All right. On the interval from -1 to 1, or in fact on any reasonable length interval, cosine and sine. Here's another recall. This is recall from, not from earlier in this lecture, but from like pre-calc, that the absolute value of sine x and the absolute value of cosine x is less than or equal to 1. Okay, so if your second derivative or fourth derivative is just a cosine or a sine, and I don't care about that negative sign outside, by the way, then you can use 1 as the value of m. Okay, so we're going to take m equal to 1. So here's what we're going to do. We're going to take our inequality here. I'm going to substitute 10 to the negative 4 for e sub t. Okay, m is 1. B minus a to the third is 1 minus negative 1 to the third. And we don't know n. That's the whole point. We're trying to find the minimum value of n needed to guarantee that the error will be less than 10 to the negative 4. Let's see. No, I already wrote something there. Darn it. Okay. Well, I guess we got to go over here. Okay. If you don't mind, I'm going to write 10 to the negative 4 as 0.0001. And that's less than or equal to, let's see, 1 minus negative 1 is 2. 2 cubed is 8. So 8 over 12 n squared. All right, so if let's see. Oh, you know what? I think I've made this mistake before. I want my error bound to be at most 10 to the negative 4. So I think, and I'm not going to be picky about this. Okay. That inequality sign there needs to be a greater than or equal to. Really, you can use an equal sign here. It's fine if you're just trying to find, because we're understanding that we're trying to find the minimum value. Okay. All right, so now if I multiply both sides by 12n squared and divide both sides by 0.0001, and let me spell out the details for anybody who might find that helpful. If you understand how this part works, you can probably skip ahead 30 seconds. We have 12n squared times 0.0001 greater than or equal, doink, doink, 8. And then I'm going to divide both sides by 0.0001. Okay, that gives me, oh, I should have divided by 12 while I was at it. Oh well, 12n squared is greater than or equal to, what would that be, 80,000? 1, 2, 3, 4, yes. All right, so now if you divide both sides by 12, you get that n squared has to be at least 6,666.67. And so n has to be at least the square root of that creepy looking number. Okay, so we're talking 81.65. Now remember, n has to be a whole number. So if this is telling us that n has to be at least 81.65, then what that really means is that n has to be at least 82. So hopefully, if you were then going to actually do that trapezoidal rule approximation, you would not be doing it by hand because that would be kind of a pain. 82 subintervals. All right. All right, so now we're going to do the same thing with Simpson's rule. As I mentioned early in this lecture, I find that Simpson's rule usually gives a better estimate than the trapezoidal rule. And so it stands to reason that probably we will not need as many subintervals to make our error small. Okay, so again, we want to find n so that e sub s is less than or equal to 10 to the negative 4. All right, so the m for Simpson's rule is different from the m for trapezoidal rule usually. It is an upper bound on the fourth derivative. Okay, so no need to reinvent the wheel. From the previous problem, we know that the second derivative of f is negative cosine of x plus pi, which means that the third derivative is regular old sine of x plus pi, and therefore the fourth derivative is the regular old cosine of x plus pi. Okay. And again, sine and cosine are bounded in magnitude by 1, since the absolute value of cosine whatever is always less than or equal to 1, we can use 1 for m. Okay. All right. So using our inequality up here, we want to find n so that 0.0001 is greater than or equal to 1 times 1 minus negative 1 to the power 5 over 180 times n to the fourth. All right, so we have 0.0001 is greater than or equal to 2 to the fifth is 32 over 180 n to the fourth. All right, so this time I'm going to be a little, well, I'm going to do a few more things in one step. So I want to get n to the fourth by itself. It's going to be on the left side. So why don't we multiply both sides by 180, actually not 180. The 180 can stay where it is. Okay, and please feel free to break this into more than one step. N to the fourth over 32 times 0.0001. Let me just make sure that that's going to do what I want it to do. All right. So n to the fourth is going to drop out there. 32 will drop out here. 0.0001 will drop out here. Oh, I should have left the 32 where it was. Darn it. Okay. Well, that's what I get for trying to be sneaky. Oh, well, you know what? I don't want to confuse you if I haven't already. Okay, let's see. So what's left over here? 180 times 0.0001. Okay, so I know what I'll do now. Now I'll multiply both sides by 32. And then I can just put a 32 here. All right. Okay, so crunching the numbers, n to the fourth needs to be greater than or equal to I closed my calculator. One moment, please. There we go. 32 divided by parentheses 180 times 0.0001, which is 1777.78. That means that n has to be at the very least the fourth root of 1777.78. Okay, now before I reveal this answer, remember that for trapezoidal rule, we needed 82 subintervals to guarantee that little amount of error. With Simpson's rule, n has to be at the very least 6.49. Now remember, with Simpson's rule, not only does n need to be a whole number, but it needs to be even. So if what you get out of this inequality is that n has to be at least 6.49, then what you need to do actually is make n at least 8. All right, and that I actually wouldn't mind doing by hand. 8 is not a terrible number of subintervals to do by hand. All right, we are almost done with this section. I just have one more thing to show you. So I mentioned that there are two situations where you might need to use numerical integration. And I actually haven't even shown you the first type. I did not do an example with a function that doesn't have an elementary antiderivative, but it works exactly the same way as in the examples I did show you. Okay, it's just that you will not be able to compare your answer to the exact value of the interval. You just have to use the upper bound estimate that we were just going over. The second situation, though, is a situation like this. So a town wants to drain and fill a small polluted swamp. The swamp averages 5 feet deep. About how many cubic yards of dirt will it take to fill the area after the swamp is drained? And we're going to use Simpson's rule. That is really sneaky. Okay, so I have to remember at the very end to write the answer in cubic yards. It's going to come out in cubic feet to begin with. Oh dear. Okay. All right, well, it makes sense. I mean, they don't do this to be sneaky. It's just the dirt is measured in cubic yards. It's not usually measured in cubic feet. All right, so I have this all set up on the tablet. So let me switch over there. This is simpler than you might think. All right, so we're just going to use the Simpson's rule formula. Let me remind you what that was. It was delta x over 3 times y0 plus 4y1. And since I only have to go up to y6, I think I'll just go ahead and spell it out. 2y2, 4y3, 2y4, 4y5, and then the last one will just be y6. All right, and in a problem like this, the y0, y1, y2 numbers are going to be given. And in this problem, they are given. Delta x equals 20 because that's the space between the measurements. All right, so the surveyor that measured this swamp, he started at one end of the swamp, measured across, and then he walked 20 feet, measured again, walked 20 feet, measured again. So that would be our value of delta x. Okay, now keep in mind, this is going to give us an approximation for the surface area of the swamp. But then we'll be able to pretty easily get what we need to know out of that. So this is going to be 20 over 3 times 146 plus 4 times 122. I don't like to use the multiplication dot when I'm doing stuff like this because it can be confused for a decimal point, right? All right, so I'll just write it like this. 4 times 54 plus 2 times 40 plus 4 times 30 plus 13 So I will go ahead and crunch those numbers. All right, so what I got was that the surface area of this swamp is approximately 8,100 square feet. Okay, but what we really want to find is the volume of the swamp. So remember, it said that the swamp averaged 5 feet deep. So we're going to use this formula. I don't know how much you've had to use this, but if you want the volume of a regular solid, that's just the base times the height. So the base is 8,100. The height, as in the depth, is 5. So that's going to give us 40,500 cubic feet. All right, so there's just one thing left to do, and that's to convert our cubic feet into cubic yards. The last time I would have done this problem would have been about, 4.5 years ago. And I don't know if I remembered to convert the answer to cubic yards at the end. Maybe I did. But when I was reading that problem, I felt like I was just noticing that for the first time. So how do you convert 40,500 cubic feet into cubic yards? Well, one way to do it, if you don't know off the top of your head how many cubic feet are in a cubic yard, is to just multiply by 3 factors of 1 yard over 3 feet. Because there are definitely 3 linear feet in 1 linear yard. So if I do that 3 times, then I can take my cubic feet and cancel it out with all 3 of these. And so apparently what I need to do to convert that into cubic yards is to divide by 27. And that comes out to, gosh, what a nice, pretty answer. 1,500 cubic yards of dirt. All right. And that's going to do it for section 8.7. We'll see you next time.